Let's talk about equilibrium. I will introduce the topic with this cartoon. A lot of the other school bus drivers complain about kids fighting and fooling around on the bus. Phooey, I never have any trouble. If you just go fast enough, they stay pinned to their seats. Now, all of America laughed at that cartoon, but not all of America was laughing for the right reason, okay? If you go really, really fast, are you going to pin those kids to their seat? No, you can go 1,000,000 miles an hour. If it's a constant 1,000,000 miles an hour on a smooth road, they don't know they're not in their living room. You got to accelerate to pin those kids, okay? That's what you got to do. Now, when I talk about equilibrium, it's the same as talking about balance. If I lost my equilibrium, I've lost my balance. And the definition of equilibrium can either be that all the forces on the object are balanced, there's no net force, or you can define equilibrium as something that has zero acceleration. And I hope everyone sees that those are exactly the same thing by Newton's second law. Now, some of you are architecture majors. I'm sorry. Those of you that are architecture majors, they're going to start to look more and more haggard as the semester goes on. They have projects that go on for weeks. They don't sleep. They don't bathe. We'll know who they are. Okay? But many of the classes that you will take as architecture majors involve what's called static equilibrium. Because when you're building a house, you would like the house to not accelerate. Unless it's a mobile home. So you're going to be doing a lot with these equilibrium ideas. Now, let's look at some examples. A rocket ship has lost all of its thrusters and is now hurling helplessly out into deep space at a velocity of 5,000 meters per second. Is this rocket in equilibrium, yes or no? Yes. Yeah, if it's a constant 5,000 meters per second in a straight line, that's zero acceleration. Here's another one that we've encountered before. Jeff is trying in vain to push a large freezer of elk meat across the garage floor. It's a Montana problem. The mass of the freezer, including contents, is 250 kilograms. The coefficient of static friction between the freezer and the floor is 0.8. Jeff is pushing with a horizontal force of 1,000 newtons, but the freezer will not budge. What is the magnitude of the frictional force acting on the freezer? And you've got these formula on the front of your exam. So tell your neighbor, what is the magnitude of the friction force? Okay. If you reach for a calculator, you're confused. Okay? There is no calculation necessary. This is just balance. I mean, Jeff pushes with 1,000 newtons one way and it doesn't go anywhere. The friction must be 1,000 newtons the other way. It's that simple. Now, those of you that reach for the calculator, you're using this formula right here, which is not a formula, I repeat, is not a formula for static friction. It's a formula for the maximum value of static friction. If I had asked, how hard will Jeff have to push in order to break these surfaces free of each other and get this thing to start moving? Then I would plug into that formula, and the answer would be 2,000 newtons. Jeff would have to push with 2,000 newtons to get this thing to start moving. Okay?